This is my email. So really, I have one important question: is how to provide seminars, because if so, half of you are here and half of you are online. So I don't know how to do it better, but I'll try. Okay, so this is the second part of the course of combinatorial graphs, and so you will teach the first part in the previous semester, yes? And by Alexander? Okay, so I don't know how much I need to remind you of the first semester, because I want to start, so we'll be teaching some advanced concepts of combinatorics and graphs, and so try to start. So, but if you have any questions, we can I can remind you of definitions and properties. So we're familiar with some combinatorial identities. Okay. Do I need to remind you what is arrangement and combinations? Like
permutation?
Yeah, permutations, arrangements. Do you familiar with this? No?
Yeah.
Okay. And so we have, if we have a finite set of n elements, then we can have exactly n factorial permutations of these elements. And if we want, so we have arrangements and combinations. And arrangements, if you think when you take the some elements of the set and you bother about the arrangement of these elements, so the order of these elements, and you can also look at this as tuple. So if you have k arrangement from this set, how many arrangements you can get? Do you know the formula? And just k will be getting here. So if you need to take k arrangements, so for example, we have, I don't know, 5 element set, and you want to get the list of all 2 arrangements. You see, so you can just take AB, BA, AC, CA, etc. So you care about the order. So this is the ordered tuple of 2 elements. How much do you can get? Can you get? Yeah, it will be. So here will be 5 factorial over 2 factorial. So it will be no. So not. Yeah, 5 minus 2 factorial. Yeah. So it will be 20. And the formula a and k is n factorial over n minus k factorial. And if you talk about combinations, it is similar to arrangements, but you don't care about the order. You can consider them as subsets of a element set. So if you have, if you consider k combinations from A is the same as k subset of A, and so the number of all different possible subsets, k subsets of A, subsets of k elements, is n use k or n factorial over k factorial over n minus k factorial. Yeah. Okay. And I want to talk about some. So here is a little bit. I think I need to be clear. When we talk here about arrangements and combinations, we consider only arrangement and combinations where all elements are distinct. So, for example, here I can took AA as arrangement. So we may talk about arrangements and combinations with or without repetition. So here I'll talk about arrangements and combinations without repetitions, and with repetitions the formula will be different. We will talk about this later. And so we have some combinatoric identities. So for example, here we have, I will write the list of some identities and you will say which of you are familiar with. So for example, n choose k is the same as n choose n minus k, n choose k plus n choose k plus 1 is n plus 1 choose k plus 1. If we summarize all the possible combinations of n choose 0, n choose 1, and so on, do you know what we get here? Yeah, 2 to the power n. Also, we can write the same formula, but with alternation. So here the last coefficient will be minus 1 to the power n. Do you know what we get here? To be precise, we should write 0 if n greater than 0 and 1 if n equal to 0. And we can for example, this one. So what if we summarize the square of all possible combinations? Do you know what we get here? Sorry? No. Okay, we'll get this later. Okay. So do we prove anything of these identities in the first part of the course? No. Do we prove these identities? Yeah. All of them? Yeah. Okay. And how do we prove 3, for example? We prove the 3. A triangle, Pascal triangle. No, not a triangle. 3 choice. Okay, let's briefly discuss the third identity. We can prove it So I know like 3 different proofs, I think. So first of all is binomial formula. Which stands that if you take a plus b to the power n, so then we get a to the power n plus n choose 1 a to the power n minus 1 times b plus n choose 2 a to the power n minus 2 times b squared, and so on. So the arbitrary element of this summation will be n choose k a to the power n minus k b to the power k, etc. And the last will be n choose n to the b to the power n. Do you prove this formula? I don't know. So calculus. And how do you prove in calculus? Yeah, of course we can. So do you see that this formula? So from this formula we can get this in one step. Yeah. How? How? The third one and the fourth one too. Yeah. So how to get the third one? Yeah. So you can get from, if you have binomial formula, you can get a equal b equal 1, and here we have 2 to the power n. Here I don't write it, but I can n to 0 is equal to 1, so I can easily write this as a first element. Okay, and also we can, and how do we get force from this? So we can get free input. We can take a equal to 1 and b equal to minus 1. So we get n choose 0 times 1 to the n power plus n choose 1 times 1 to the power n minus 1 times minus 1 power 1, and so on. N choose k times 1 to the k minus k power minus 1 to the k power. And the last will be n choose n times minus 1 to the nth power. So if you forget about ones, we can just get this alternating sum. And so this is equal to 1 minus 1 to the nth power, which is of course 0, except for one case where n is equal to 0, because if n is equal to 0, we'll have 0 to the 0 power, 0 to the 0 power, and we don't know what this number is, but we can just, if n is equal to 0, we just can calculate the sum. Just look at this will be just n over 0, and 0 over 0 is 1. So when n equals to 0, this is 1, and when n is greater than 0, then this alternating sum is equal to 0. Okay. Okay, how do we prove it? Oh, first idea is using induction. Also, we just can. In every formula where you can get a combination, you can just look at this structure and try to find what we choose of what. So if we have here n choose 2, then here we can see the two combinations of n element set. And here, if you look of this product, then you can see that we have exactly n brackets. And from these brackets, what do we choose for? So for example, we want to calculate the coefficient before the a to the n minus 2 power times b squared. And so where we can see the two combination of an element set. So here's the number of two combinations from an element set. So we have n brackets, and we need to choose exactly two brackets where we can take b, and n minus 2 brackets where we can take a. And these brackets are ordered, so we can just number it. So this is the first bracket, this is the second bracket, and this is the last nth bracket. And if we choose n minus 2a and 2b, then we can just choose the number of brackets from which we can take b. And so this is just two combination from an element set. So here we will have n over 2. Okay, and so this is called for each case. So for each case, so if we look at this coefficient before the a to the n minus k power times b to the k's power, we just need to choose the key brackets from which we choose b. And if we choose this brackets, so it is combination, because we don't think about the order here. We just need to choose the subset of k indexes, and from these indexes we take b, and from the other we take a. And so we can prove the binomial formula just looking at these brackets and use the definition of combination. Okay, how can we prove this formula another way? Well, for example, we can look at I think this is similar to what you're talking about when you're talking about the trees. It's called Pascal Triangle. And so this is a triangle where on the border of this triangle we just put ones, and then we holding the following rule. So if we want to find the number in the newest line, we just take the sum of the two numbers above this element. So this element will be sum of this 1 and 1, and so here will be number 2. Here we have two new numbers. And those three will be 3 as sum of 1 and 2, and also 3 as sum of the 1 and 2, and so on. So here we can write 4, 6, 4, and so on. So each number in this triangle, so if you have x and y, x and y, then the number in the next row will be x plus y. And it's not very hard to see that this Pascal triangle is exactly the number of possible combinations of an element set. So Pascal triangle is, we can write this as 0 choose 0, 1 choose 0, 1 choose 1, 2 choose 0, 2 choose 1, 2 choose 2, and so on. So do you understand how to prove that this triangle is exactly the number of possible combinations? So it's clearly true because if you take n choose 0 or n choose n, it will be 1. So in the end of each row we have ones. And for example, I don't know. So for example, look at this number. This is 0, first, second, third, fourth row, and the second element of it. So this should be equal to 4 choose 2, and this is 4 factorial over 2 factorial 2 factorial. So yeah, okay, this is correct. So for example, for this number, this holds. So I want to prove. So if you take the case element in nth row, if we count it from the 0, then we'll have here the binomial coefficient or Ilyinsky combinations. This is the same things. Okay, maybe you're familiar with the following example. So imagine that we have a city, and with streets and avenues that go only from the south to north and from the east to west. And suppose we want to go from the lowest left point to the upper right point. And we, of course, want to get as fast as possible, so we go only north and east. And do you know how many possible ways going from this point to this point? Maybe you're familiar with it, no? Yeah. 2 to the power something. Okay. What? So for here I have, so I need to go here 5 steps to the right and 4 steps to the up. So 9 steps. Okay. So how to count the number of possible ways? you can think of so this task is familiar with this one, because if you just try to, so you can just calculate all this all the steps. So of course, if you want to get, for example, this point, this is only one possible way, because you just go one step up, and this one is also only one. Also one possible way, because you get one step right. And here, if you want to get here, you can just summarize the number of possible ways to go in here and here. So here will be 2, and you just can calculate it, just counting the number of ways of you going through the all intermediate points. So here we have 3, 4, 5, and so on. And so this is this picture is the same picture as this, but we just need to rotate it, yeah, because here we have the same principle. When we put here a number, we just summarize the number of the numbers over it. So so actually, if you look at this number 6 here, it's nothing but the number of ways of getting from this point to this point, if you want to go the diagonals, diagonal left or diagonal right. So this is the same problems. If I prove that this is the combinations, this so this is the binomial coefficient, then this guy is also binomial coefficient. Okay, so I need to go 4 steps up and 5 steps right. So I need just to try to order them somehow. So I need to I can go for example, 4 steps. First, I want to go up, and then I want to go right. Oh, first I want to go right, and then I want to go up. And so I need calculate all the possible permutations of these ups and rights. Yeah. And so how can I calculate it? Yeah, it will be a combination, but why? It will be yeah, it will be it's the same because n over k is the same of n just n minus k. And also you are familiar with this notation, or just you write c of n just k? This or this? Both of them. Okay, because I don't know. Okay, I can use both of them. Okay, so you have 9 steps here, and you want to choose, for example, which of steps are going up. So you have here 9 places, and you just take the 4 of them which are going up. And so this is combination, because all you need to do is just take the 4 subsets of 9 element set. So you can just again write the number of the steps, and you just here we choose the 4 element subset of it. So this 4 element subset, and these are exactly the steps where we're going up, and the other steps we're going right. So the number of possible ways are going from here to here is just the number of combinations of 4 combinations of 9 element set. And the same holds in arbitrary situation here and here. So if you want to find what this number is, you just calculate how the number of ways of going from this point to this point, going to the right or left. And so I prove that in Pascal Triangle, actually we have the numbers in Pascal Triangle is actually the number, the binomial coefficients or combinations. We can prove this the other way, because the main rule of Pascal Triangle is that we summarize some numbers here. So if we want to find, for example, the number 6, I want to summarize 3 and 3. So if you want to get the second number in the fourth row, I need to take the sum of the second number in the third row and third number in the third row. So we counting so first and second, and so I can just so if I already proved that this row is consistent of binomial coefficients, then I just take the sum of these binomial coefficients. And here I can use one of the identities that I write in the beginning of this lecture. Because if we look at the identity n choose k plus n choose k plus 1 is n plus 1 choose k plus 1, this is the same as this rule. So if I take, so this is the first element in the third row. This is like a second element of the third row. And if I summarize them, I will get the third element in the fourth row. And so if I can prove it by induction. Yeah, so I just look at this, it says that this is the binomial coefficient, and this is the binomial coefficient, and so all the ones are binomial coefficients. And then if I want to take arbitrary number, I just look at the numbers above him and just use the identity formula, the formula for the binomial coefficients that I write in the beginning of the lecture. Okay, so we prove that this triangle consists of the binomial coefficients. And how can we calculate the sum of the elements in this row? I want to prove that the sum of these elements is 2 to the power of n. So remember that so if I choose, for example, the fourth row, what this number states about? These numbers are just possible ways of going from the upper point to the fourth row. And I'm going to the left or to the right. So the sum of these numbers is the all possible ways of going 4 steps from this point. So I have these 2 types of errors, going to the left and going to the right. And I have 4 steps. So first step will be going to the left or going to the right. Second step will be going to the left or to the right. The third step will be going to the left or going to the right. And the second step will be going to the left or going to the right. And so if I have this possible variations, so how many variations I can choose the one of the 2 possible steps if I have 4 steps? Why? Yeah. So I have 2 possible things to do here. two possible things to go here, to do here, and this is independent choices. So I can go here to the left, and here to the right, and here to the left, and here to the left. So I can just take the product of them. Yeah, and so totally will be exactly 2 to the power 4 possible ways of going left to right. And the same holds for the nth row. So, well, if I take nth row, then the number of elements in the Pascal triangle will be equal to the 2 to the power n. So I just gave you another proof of this identity. Okay, I think we'll discuss now the first identity on the Pascal triangle, and we'll have a little break. I need to close the door, I think. Okay, can we calculate this alternating sum? Oh, I just closed the door again. Can we calculate alternating sum using the same picture here? So we need to I will write additional rows to see the difference. You can see that for odd rows, first, third, fifth, if we look at the alternating sum, then it is easy to see that all will be cancelled to 0. Yes, because we see that we have the symmetry here. We have the symmetry here exactly the same way, exactly the same as the first identity. So n choose k is equal to n choose n minus k. So if you take the k subset of the n element, is the same as they take the n minus k elements. You just can take the additional elements to this k to form the whole set. So if you have the symmetry, of course, if you take the alternating sum, so for example, here you have plus 1 minus 3 plus 3 minus 1. Of course, they will be canceling each other, and so the alternating sum of these odd rows will be equal to 0. But can you see why, if we look at the even rows, then we also will have 0 here? So for example, here, if I took 1 minus 4 plus 6 minus 4 plus 1, then I'll have 8 minus 8, 0. But how can we see it from the structure of the Pascal triangle? I think maybe someone has an idea for this. we want to prove the first formula. So we want to prove that if we take, well, for example, here 1 minus 6 plus 15 minus 20 plus 15 minus 6 plus 1 is equal to 0. But we want to prove that this is 0 using the main property of the Pascal triangle. So why if you have this alternating sum, why yeah, we have this in the odd rows. In odd rows, we have that this guy is minus this guy. So if you write the sum, they will all cancel to each other. But here we have that, for example, C x over 1 is equal to 5 over 6, 6 under 5. So these guys are equal to each other, and they with the same sign. So they both negative. So they will not cancel here. But what is the main property of the Pascal triangle? It's that if we look at this number, so each number in this row is the sum of numbers from the previous row. How we can use it to prove that this all will be equal to 0? We don't need. We just need this rule. But maybe I will. So let's use this rule and wrote not 6 but 1 plus 5 here. So we have 1. Here we have 1 plus 5. Here we have 5 plus 10. Here we have 10 plus 10. Here we have 10 plus 5. And here you have 5 plus 1 and 1. What happens if I now look at this sum, alternating sum? Yeah, of course, because each number in the previous row occurs exactly 2 times, one with minus, one with negative sign, one with positive sign. And so they will cancel. So, for example, this 5 is, we can meet it there and there. This 10, we will have it here and here. Here with plus sign, here with minus sign. And this holds for the all numbers. So it will be 1 minus 1 plus 5 minus 5 plus 5 plus 10 minus 10 minus 10 plus 10 and so on. So of course it will be equal to 0. So just using this property of the Pascal triangle, or if you choose just using this identity, so if we can forget about the Pascal triangle and just use this identity. So if we look at the sum and just write each member of this alternating sum in terms of the previous binomial coefficients, so here will be something like n minus 1 over k, choose k, plus n minus 1 plus choose key n minus 1 choose key plus 1 equal to n choose key plus 1. And so if we change each of these some elements to the sum of these two binomial coefficients, then we can see that they will all cancel each other, and so this whole sum will be equal to 0. Of course, it is greater than 0 because here we have, so here we have in 1 is n equal to 0, and for the all other rows we will have in 0 as the sum of the alternating formula. Okay, I think we will take a little break, about 5 or 10 minutes. So maybe we'll continue now. I want to make like two small announcements. First of all, about the literature of the course. Usually, I have a Google Drive directory where I can put all the books that you can read or find something about the combinatorics and graphs, and so you just can write me, email me, and I can send the link to this Google Drive. So also, if you need something to discuss, we can write me an email or write me, in Telegram, because the previous group just make a Telegram channel and discuss all the questions there, but I can discuss it by email if you want. Also, as I said before, I don't understand how do I need to provide the seminars if you have some students online and some students here, because usually so I think we will discuss this identity now in about 10 or 15 minutes, and then I'll just write some more identities, and you can ask me privately about them, and we can just discuss them later. In the previous course, I give some 2 or 3 or 4 homeworks, and there was some midterm and the final term. So I know how to final control work, final exam. I know, because I think in this course we have this is called zachot. So we just have. So in the previous course we have in the previous year we have 2, 3 or 4 homeworks, and then we have 2 control works, midterm and final. And this will be, so I just calculate the number of points, and then this will be your final mark of this course. But I thought that if we have, in the previous year all things were online, but now I can discuss with you here some tasks. So I think we will have some, I will count some work in the auditorium, but I don't know, I need to wait for all the students to come here, I suppose, I don't know. Because I hope that they will be here by the middle of October, or I don't know how, when do they come to Russia? Do you know? Do you have any information? No? Yeah. So I don't know. I think we'll start with some homework. So I will just we'll discuss problems here, and then in the middle of September I will just send you some homework, and you can complete it and just send me by email, or we can discuss it later. Okay. Okay. So, do you understand all we're talking about in the previous hour? Or maybe I just need to. You have some questions, maybe no? No. Okay. So we can just continue to the fifth identity. So this is not similar to the previous because previous was just the using the previous principles, and if you here we have the square of the binomial coefficients, and on the first look we have nothing similar in the previous identities that we can start. But so if you have the identity that you don't familiar with, first of all we can just try to find the answer just by calculating. So for example, if you take I don't know, for example, n equal to 3, then we have this was in the previous year. I think that the more or less will be the same, but maybe I can provide some. So it's very hard to organize the control work when all students are online. So if you all be here, we just can cancel the midterm and just provide the small tests every week. So for example, for half an hour, I would just give you some tasks similar to what we doing on the previous weeks, and so we'll not doing this midterm or final exam, or just every time we will have 30 minutes for you to just do 2 or 3 tasks. I don't think so. I don't think that we need to doing this hard work and spend 3 hours to solve some problems. So I don't know. We'll see if all students will be here by the middle of October. Then we can just do the test. So we'll discuss later. Yeah. So here we have I just take the row in Pascal Triangle, just calculate the square of it. Here we have 1 squared plus 3 squared plus 3 squared plus 1 squared, and this will be 20. For the second row, I'll have 6. For the fourth row, I'll have 16, 16, 36, 70. Right? So if you look at the Pascal triangle, then you can find all the numbers. So, for example, I can take, so this is n equal to 2, n equal to 3, n equal to 4, and for example, for 1, it will be just 2. Okay, so 2 we have here, 6 we have here, 20 we have here, and 70 we have here. So you can see that there is a correlation, yeah? So what I need to write here, which binomial coefficient I need to write here? Yeah? You just can calculate. So this is for n equal to 1. Yeah, but what is, so n equal to 2. For n equal to 3, it will be here. So we just need to find the function of n here. What is the, so we need to find the number of the row and the number of elements in this row for each of these. So I don't think it's very hard.
Cn minus 1 over 2.
That's to n. This is right, because we have this is second row, this is fourth row, this is sixth row, and this is eighth row. Remember that we numerate elements from 0 here, because binomial coefficients are numerated from 0. So for example, here we have 0, 1, 2, 3, fourth element of this row. So what should I write here? Just? Of course. Yeah, okay. So here we have first element in the second row, second element in the fourth row. So this is 4 over 2. This is 6 to 3, and this is 8 to 4. Okay. So we get the answer. How do we prove it? This is again 2 or 3 different possible ways of doing it. Okay, the first idea, as I told you, is looking at the binomial coefficients. Where can we see binomial coefficients? So 2n over n, 2n where we can meet this. So if we take x plus y to the 2n's power, and then we open the bracket, then somewhere we have 2n uh, 2n over 2n choose n to the x to the nth power and y to the nth power. And how can I get these coefficients? How can I get formula from this coefficient? I can just look at this power and try to write the different formulas. So if you look at the 2n choose n, or for example, if you just look at the definition, so you have 2n elements. And you want to choose the n element subset from these elements. So I want to choose an element subset. But if you look at this formula, this all guys are doing with n. So the formula idea will be looking at the, for example, first n element, then the second n element. And this I can do the same trick and look at the, so I can just write it as x plus y to the power n times x plus y to the power n. Okay, thank you. So what if we just open the brackets here, and so we have like this sum of the binomial coefficients. So we have to use the binomial formula here, and then use the binomial formula here, and then open the brackets. What coefficient will be before x to the nth power and y to the nth power? I will give you, so for example, we can do this to the power, for example, 2 or 3, and see what we can. So for example, n equal to 2. So we have here plus 4 choose 2, x squared, y squared. But if we write this as x plus y squared times x plus y squared, and open the bracket here, and open the bracket here, then how can I get x squared y squared? So I can get from this bracket x squared, from this bracket y squared. So here I can 1 times 1, or I choose y squared here and x squared here. This also will be 1 by 1. And in the middle, I can get xy, and here we'll have 2 times 2. And so we see that these coefficients here come as the sum of the 3 squares. Exactly as we have in this formula we want to prove. So can we do the same in the arbitrary situation for each n? And so if we can do this, then we can prove this formula, this identity is at the root. So all we need to do is just to try to make the same calculations, but for n instead of 2. Maybe right here. Okay, so maybe you have any questions? Or you just you just need to. So I just wanted to write the same formula, but in arbitrary, so for arbitrary n. Okay, so maybe we can do that together. So here we'll have like n choose 0 x to the power n plus n choose 1 times x minus 1 n minus 1 and so on. And the same will be going here. Okay, so how can we get?
Yes, in the first expression,
Yeah.
we will start from the beginning, but in the second one, from the end.
Okay, yeah, so here we have, we want to take the this guy and this guy, yes? So he will have n choose 0 times n choose n, yes? Okay, the next will be n choose 1, n choose n minus 1, and so on. And the last one will be
N choose n.
Yeah. So it is similar to what we need to do, but here we have the different formula. Are this formula the same as here?
Almost.
Almost.
Yeah.
And what is the difference?
Just didn't express it in.
Yeah, but this is the same formula as here, or no?
Yes.
Why? Yeah, totally the same, because we just need to use this formula, and then we just need to use one of the identities that that I write in the beginning of the lecture, because we know that n choose k is the same as n choose n minus k. Yes. So if we do this for all summands, then we'll have the formula that we need to prove. So I told you that this is a tricky one, because the more the most simple one will be not this formula, but this formula. And so in this expression, this formula has more sense, because I just can explain it not using the binomial formula, but just using the definition of binomial coefficient. Because if you have two n elements and you want to choose n elements, you just can divide it by two parts: the first n elements and the second n elements. And if you need to choose an element from the whole set, you just choose the k elements from here and n minus k elements from here. And so if you want to calculate the number of possible ways of choosing k subset here and minus k subset here, it will be just the product of n choose k times n choose n minus k. And then I just summarize it over all possible k's, which will be from 0 to n. And I will have the same formula. Yeah, okay? And you can see here that also we don't need these parts to be the same. And we can generalize this formula by writing something like n plus m over n will be equal to n choose 0 times m choose n plus n times 1 m n choose 1 times m choose n minus 1 plus etc. plus n choose n m choose 0. But here I need to be the m where m is equal or greater than n. Yeah, because it's the same idea. If you have n plus m elements, I can look at the first n element and the last m elements, and then choose. If I want to choose k element here, I just need to take k elements from here, elements k from here, exactly. And also we can we also don't need this to be the same element, so I can write, just take the, for example, k elements here and write this formula. I just need to kb, so here I need to mn be greater than k. So I can generalize the fifth identity to this arbitrary identity. It says the idea that I can just divide my set into two pieces and just try to calculate how many combinations I can get from these two subsets in the whole. Yeah.
Plus m minus k. Here you go. Second.
This one.
No, I mean this one. The second one, n minus k.
Because if it corresponds to the last formula, then we choose k here and sorry. If this formula holds that when I can choose like j elements here and k minus j elements from here. So I just so I want to choose k elements from the whole set, and I just ask myself, so how many elements are from this part and how many elements are from this part? So I have several possible situations. So from this part can be 0, 1, 2, etc. And the maximum number of elements I can choose from this subset is k elements. Yes. And so if I choose 0 from here, then I need to choose k from here. If I choose 1 here, then I need to choose k minus 1 here. And so I just need to. This is all possible situations. This situation where I can 0 elements belongs to the first part. This is a 1 element belongs to the first part, and so on. And so I just summarized all these possible situations, and in each situation I just take the combinations in this part and multiply it by the number of combinations in this part. And so I can get this formula. Okay, I think I will just, now I'm writing some additional identities, and you can just try to prove it by yourself and discuss with me, and maybe we can discuss them together in the end of the seminar. So I'll continue the. Okay, I think I will give you 10 minutes for each of these identities, and then we can discuss it together. No. We see that 2 to the power n is the sum of all binomial coefficients, and here we have only coefficients where the lower number is even. Okay, I think if you want to, so if you know the proof, you can go to the board and just explain your proof. I can, of course, you can take a guess, but yeah. So you can just discuss with me your proof, or you can go to the board and explain to all other students what you prove, because of course you can just take the first 5, so n equal to 1, 2, 3, 4, 5, and just find the answer. Just don't take a guess. Don't take a guess. Okay, if you want, I can give you the answer, but it will not help you to prove it. I think I can write all the possible. If you have any questions, you can ask me now, because if you don't understand any part of the lecture, you can just ask me now, because it's better to ask. Okay, I'll give you. Okay, I'll have. You know. Sorry. It's
Just half of the Pascal triangle.
yeah, it's almost true, because it is 2 to the power n minus 1 if n is greater than 0, and 1 if n is equal to 0. Because if you have n equal to 0, then this formula doesn't work. Doesn't work because 2 to the power minus 1, it is not equal to 1. Yeah. And so who can prove it?
Can be proven by induction.
It can be proven by exactly several ways that we can do it. We can prove it by looking at
Pascal Triangle.
yeah, Pascal Triangle. It's like some through induction. We can look at this and these two guys and try to use them to prove it, as you said. So whatever you like more. But okay, can someone explain the proof? Prove it? Maybe no.
I have like one conclusion.
Yes. Well,
When we try to prove it by Pascal Triangle, is it considered a how can I say, solid proof?
of course, because Pascal Triangle only the Pascal Triangle is only just visual imagination of binomial coefficients. And all you do in Pascal Triangle is just using this identity that sum of the two binomial coefficients is the third binomial coefficients and nothing else. So, okay. So, okay. What was the idea about using this and this identities?
If you this third one, there's I read that there's 2 choices.
Yeah, but yeah, we just can look at the mean or half sum of the third and fourth identity. Yeah. So if we summarize these two guys, then we will see that all the even elements are cancelled, and so all the left is exactly the binomial coefficients where the lowest number is even. So if we have the half sum of the 3 and 4 identities, then we can we can get that and so this is half of the 2n plus 0 if n is greater than 0, and half of the 2n plus 1 is n equal to 0. So this is will be 1, and this is 2 to the n minus 1. Okay, let's look at the Pascal triangle. So, for example, here I have the sum of these 3 numbers. Can I somehow describe it as using the main property of the Pascal triangle? What I can say about some of these 3 numbers?
counting how many ways to arrive at those three.
Yeah, for example.
Or maybe sum of elements from the one step.
Yeah, of course. If you look at the previous row, so how these numbers in the previous row occurs in these three elements. So, for example, this number 10, it is just sum of these two numbers, yes? This is the sum of these two numbers. And this is just this number. So sum of these three numbers is nothing but the sum of all numbers in the previous line. And so this is just the number of all binomial coefficients, but in the previous row. And this is of course equal to 2 to the power n minus 1 by the third identity. And so this is the actual proof, because I can just write the sum and just use the identity, the main identity of Pascal triangle. So I can write this. So this is just equal to n minus 1 choose 0. This is the n minus 1 choose 1 plus n minus 1 choose 2, and so on. So here I will get the sum of all binomial coefficients with the base n minus 1, and this will be equal to 2 to the power n minus 1. Except for the case where n is equal to 0, because here we can go to the previous row. Actually, I can ask so interesting formula will be if you not looking at the even numbers, but only the numbers are divided by 3, 4, and so on. But this is, I think, the may be difficult to you. But if you want, you can, for example, try to find it like this sum. So sum of each third binomial coefficient, but it is hard because it's used. I don't know if you're familiar with the concept of complex numbers, and if I think I can just say a few words about this formula if in the next lecture if you want. And so it's not very hard, but I don't know what you know about complex numbers, but it will help you to find this sum or just so if you want to calculate it. For each case, not the sum of all binomial coefficients, but sum of some part of it. You can just use the same idea here. Okay, let's go to the next identity number 7. Do you need a hint here?
No? Yes.
Okay. We have. If you look at this formula, you can see that so you cannot use like the Pascal triangle here because we have some strange coefficients, yes, and we just can they're not helping us. But can we somehow change it? The first idea is just look at the formula like n plus k n factorial over n factorial times n minus k factorial. And so here we have in the denominator some factorials. So maybe we can just rewrite this number into some, rearrange this, so include these two in this binomial coefficient somehow, so that we can get buzzer of these different numbers here. And the second idea is just try to look at the somehow something similar to the binomial formula. Try to look at this as this function. So I just so this formula is this function when we take x equal to 1. So maybe we can do something with this function to get rid of this ratios. Oh, I think. So maybe I think that maybe I need to look at the similar function, but you will have, maybe this will make better when we have x squared over 2, x cubed over 3, and so on. Yeah. Need some help?
All this 1 divided by 2, 1 divided by 3.
Okay.
It has this space.
Yeah.
So you cannot like just put it in front of it. No.
Yes, something like that. So I just want to. So here we have 1 over k plus 1 and plus k. Yes. So I can. Yeah, I can write this k plus O. So I have k plus 1 times k factorial is k plus 1 factorial times n minus k factorial. So I can make from it another binomial coefficient. Yeah. Yeah, exactly. So I can multiplicate and divide by 10 plus 1. And so here I'll have new binomial coefficient. But now this ratio will be the same for the all summands. Yeah, because I will have 1 over n plus 1 everywhere. And so I just can get rid of it and just look at the sum of these binomial coefficients. Just calculate the sum of these binomial coefficients. Yeah, I think you can. This is what you mentioned about something like this, no?
How does you like the first term is n
Yes.
by 0, 1 and half. And
Yes.
all of this space, like
Yes.
beginning with it, have this space. What?
Why do you have n plus 1 factorial in the denominator? It's the last one.
Yes, the last one.
Yeah.
Is like this.
Yes.
And the first one is the same like this. So if you put.
But the first one is just n.
If you put 0, it will be 0 factorial by 0, 1. So it don't have.
But what about the second summand? Is 1 over 2 times n choose 1, and where we can have n plus 1 factorial in the denominator? In the second summand will be 1 over 2 times n choose 1. Yes.
So it will be 1 choose. Will be 1 by half.
Yes, 1. Yeah, but
and then the second. Only this.
Yeah, but we'll have n So it will be n over 2. Yeah, but not n factorial over n plus 1 factorial. So the second summand will be n over 2. Yes, not n factorial over n plus 1 factorial. Oh, maybe I don't understand what you're saying. First summand will be equal to 1.
The second term
Is equal to n over 2.
Third.
Yeah, but it's not a factorial over n plus 1 factorial. Yes. But what is the answer of?
so what I'm saying that all of it is that this one by half on the third it has this phase.
If we have n plus 1 in the denominator, yes, but what is the answer? Yeah.
The right answer.
Yeah, yes, this is right. Yeah. Okay, so I already saw the correct answer here. So if you use this idea, then it is not hard to say that we can write it as 1 over n plus 1 times the coefficient. So here I will it just n plus 1 over k plus 1, just k plus 1. So I need just write n plus 1 over 1 plus n plus 1 over 2 and so on plus n plus 1 over n plus 1. And I think you can all calculate this one. It's just similar to the third identity, yes. And this is just 2 to the n plus 1 minus 1 because we don't have here the first element of this. And also, if you look at this function, how can we get rid of these ratios? You can just take the derivative. So the derivative will be equal to n over 0 plus n over 1x plus n over 2x squared and so on plus n over n x to the power n, because if you take the derivative of the x to the n plus 1 of the power n plus 1, then we have n plus 1, and this will be cancelled with these ratios, yes? And this is nothing but 1 plus x to the nth power. And so if you need to find the f of x, you just need to try to take integral of it. And if you know how to calculate the integral, then you know that integral of 1 plus x to the nth power is 1 plus x to the n plus 1 over n plus 1 plus some constant. And so all we need to do is try to find this constant. So I take x, I take this x equal to 1. I have 2 to the n plus 1 over n plus 1 plus some constant, and this constant we will find it if we just take here x equal to 0 and try to find the constant. This will be minus 1 over n plus 1. Okay? Okay, so let's do the last one. And maybe I will try to help you and draw an additional picture. What we're actually counting here. So for example, we starting from the any element, for example this one, and then we take the element from the next row and go to the right. So I just take this element, the next element, the next element, the next element, and just stop somewhere. So this sum is just the sum of elements on the diagonal of the Pascal triangle. So we can take just the part of some diagonal and try to count the all numbers in this diagonal. And I will start with this formula the following lecture, the next lecture, and we will try to have some identities from here. So from this formula, actually we can find the, for example, sum of the squares of numbers from 1 to n, and also cubes, and so on. So actually, binomial coefficients helps us to find some formulas counting just the sum of powers of first and natural numbers. But I will explain it in the next lecture. Let's try to find. I'm going to find some formula consisting 2 or 3 binomial coefficients, I think, here. I want to have somehow rather short formula to find the sum of the elements on the diagonal on the Pascal triangle. So if you want a hint, all you need to do is just look at the Pascal triangle, or just use so somehow try to find how to use one of the identities to cancel just all or almost all the summands. Okay, so all we need to do is just so we want to calculate the sum of these elements forming the diagonal in Pascal triangle. What it means that they forms the diagonal. Okay, so let's add. So I want to add some number in this Pascal triangle to this sum. But of course, if I choose arbitrary element that I cannot use, I want to choose elements such that I can use the main property of the Pascal triangle. So if I took the arbitrary number, it doesn't help any it doesn't help me any at all. But which element I can add to the sum that I can use the main property of the Pascal triangle. So the main property is that if I have 2 numbers, that I can just use this number instead of this one, these 2, yeah? So what number can I add to this diagonal such that I can use this triangle property?
Just one, first one.
Maybe, but if I use this one, then I will have double 4 here. This doesn't help me because after that I will need to add 2 ones here. It is better to use this other option here. instead of 1, I can choose the other. Okay, so if I don't use this number, what number would I prefer to add to this sum? So we can use this property of the Pascal triangle. No? Maybe you don't understand the question. Yeah. Because so I want to add some number to these 5 numbers, such that I can use, and then I use this main property of the Pascal triangle. So if I can change these numbers into this number, yeah, and for example, this 2, I can instead of this, some of these numbers is this number, and so on. So what?
So you mean we want to change like the right ones to just we don't like harm the property of the triangle.
So if you want to summarize the elements in Pascal triangle, if you not want to use this summarizing the 10 elements, we can use the main property of Pascal triangle is just to write one element, to use one element instead of 2 elements above him. And so if we can do this many times, then maybe we can instead of writing the n summands, we can just have one. We can calculate the sum using the property of the Pascal triangle, because we can just use the Pascal triangle to calculate the sum, yeah, somehow. And so here, all we need to do is just to add some of the element of this Pascal triangle, and then if we use the property, then we can calculate this sum of this element and one more element here. No idea. Okay. Huh? Yeah, but if we take, for example, this element, it's a bad element because, okay, we know that we want to find some 3 plus 4 plus 5 plus 6 plus 7. But if we add 1 here, then all we can do is just get rid of this 3 and 1 and write here 4. But this doesn't help at all, because now we don't have any 2 elements that lies in the same row near to each other, and so we cannot calculate the sum. So this is not a good idea. Okay. So the idea is that we can add, but if if we can take this one, let's take this one. So let's add this element to the sum of these 5 elements. Okay. How can we use the main Pascal triangle principle? We can calculate the sum of 2 numbers here, yeah? It will be which number? 6, okay. The number of these numbers, okay. It's getting better. These numbers, okay. So if you add this number, we'll get this one, yes?
Yeah.
Cool?
Yeah.
So this sum is just the, so we need just take this binomial coefficient and subtract this binomial coefficient, so this will be the answer. Okay? So the sum is just nothing like something like n plus m plus 1 over k plus n minus n over k minus 1. And you can prove it not using, so if we're looking at so we can just add here n over k minus 1. And so these two guys is equal to n over n plus 1 over k. These two guys is equal to n plus 2 over k plus 1, and so on. And then just using many times the second identity, we will get here the fraction of these two binomial coefficients. Okay. So as you said, for example, we will begin the next lecture from it. So if you want to find the, for example, the sum of the first n natural numbers, 1 plus 2 plus 3 plus 4, etc. plus n, then all you need to do is just look at this binomial coefficient, because he will have the difference between this one and this one, and this one is 0. So I just prove formula of the sum of the first n natural numbers. Yes, because this natural number is nothing else but the sum of some binomial coefficients with the line on the diagonal of the Pascal triangle. But so in this case, it will be better to take another diagonal like this one, and this will be n over 2. This will be 1 over 1, 2 over 1, 3 over 1, and so on. But I will start this next lecture with these examples. Okay, understand? Okay, I think that's all for today. Yeah, I don't know, because I don't know how to, as explained before, I don't know how to provide. So I would like to provide like something mixed lecture with seminar. So I think I will, in the following week, I will again start with some. So I will prove some theorems, but I will ask many questions during the lecture. So and if you need break, you can just ask me. I think we can just make a some break in the middle of the lecture. I don't know how do you want to. So we can make breaks each hour or each half an hour, and so you just need to ask. Okay? Yeah.
So how about,
Yeah.
not about this.
Yeah.
Do you like to recommend any textbook, or we don't need it?
Yeah, so I can provide you some textbooks that I can send you a Google Drive folder where we have some books about combinatorics, where you can read about this, maybe another advanced concepts. But I don't think there's actually one textbook that follows this course, but some different experts will be using some different textbooks. So if you need some material on different lectures, you can ask me, and I will just find you the right book for it if you want. Because if you need about the identities, I think I'll prefer one book. If you need to read about graphs, of course you need some other book. Yeah, so if you have some problems, you can just ask me, write me, email me, and I will try to help you. Okay. Okay. Yeah. I will just write the mail in chat. Okay. Okay, that's all for today. Thank you. If you have any questions, you can ask me now.